So, when I have two amounts of two reactants, I have a limiting reagent problem. You have to figure out which one I'm going to run out of first. Am I going to run out of the zinc sulfide first, or am I going to run out of the oxygen first? So if I have two amounts, I'm going to have to work out two problems. And if you remember, all these problems follow the same general pattern. You start with your known. Get your known into moles of known. Once you get it into moles of known, use your mole ratios to get it into moles of your unknown, and then convert your moles of unknown into usually grams of unknown. But it could be something else. It could be volume. But usually whatever you're given, whether it's grams or liters or density, whatever you're given, get your known into moles. Then you use the mole ratio, and then you convert it into, what you're trying to find at the end, grams, liters, or whatever. So, let's start with a refresher. If you have grams of zinc sulfide on top, what goes on the bottom, Gross?
Grams of some sort.
Grams of not some sort. What's up here?
Zinc sulfur.
So what goes on the bottom?
Grams of zinc sulfur.
Grams of zinc sulfide. What do? Get it into moles. So we need to add up the mass of this thing. So zinc is 63.5. Sulfur is 32.1.
Zinc is 65.3.
That's right.
Mistake.
65.3?
0.39.
No, 63.5.
Isn't the ZN of zinc
Yeah.
65.39?
Oh, I'm looking at sulfur. I mean, copper. So it'd be 65.4 plus 32.1. Okay. So we get 97.5. Once we have it into moles, then we use the mole ratio in there. For every two of these, I'm going to make two of those.
There's the one.
Yep. I just like to use these numbers to reinforce like where they come from. But if you want to put 1 over 1, that's fine. And then we convert it to what we want to find, and in this case, we want grams. So what does 1 mole of zinc oxide weigh? 81.4. Plug in the numbers.
Should be grams.
Oh!
Ooh, boy.
What?
$348 grams of zinc oxide.
Isn't it 349?
Yes.
I was ready to do a homework mistakes.
Make sure you put your unit and what it is.
So, the second to last, box, that's just the amount of them in the equation?
Yep, this is the amount of zinc sulfide we start with.
No, the box in the middle.
This is the ratio.
Okay.
So for every 2 of these, I get 2 of those.
And so, on that, where is that?
Right here, going from moles of unknown to moles, or from moles of known to moles of unknown. But we're not done yet, Taylor. We have to mess with the oxygen. Now in the past, we were given this number in grams, like, oh, you have 15 grams of oxygen. But here, we're given it in volume. But the overall process is the same. First thing you gotta do is get your known into moles. So how do we convert a volume into moles? Well,
I use malaria.
if it was a solution, we could use molarity. That's one way, like moles per volume of liquid. But this is just a gas. So we are gonna use Pivnert. With Pivnert, we can solve for moles. We need to write down everything we know. Our temperature is 65 Celsius. Has to be in Kelvin, so we add 273.
That's not right. Three plus, 5 plus 3 is 8.
Just racking up mistakes.
Volume is 185.
Choke under the pressure.
Our pressure is 0.500 atmospheres. And then our R value. Remember, R comes in two flavors. Liters kPa per mole Kelvin, or it comes in 0.821 liters atmospheres per mole Kelvin.
0.82 or 0.082?
0.0821. So in order to find the moles, we're going to use PV equals nRT. We have our T, we have our V, we have our P. Which R value should we use in this one, Taylor?
Bottom one.
Second one. Why the second one? Because it has atmospheres and our pressures in atmospheres. Now we can plug in the numbers. Times our volume divided by our R value divided by temperature, and then I get my moles of oxygen. I get 3.33 moles of oxygen. And I'm not done yet. I have to, once I got into moles, now I go from moles of known to moles of unknown. And I use my ratio. For every 3 of these, I'm going to get 2 of those. For every 3 moles of oxygen, I get 2 moles of zinc oxide. Bless you. And then the last step is convert moles of known to grams of unknown. 1 mole of zinc oxide weighs 81.4 grams. And they get 181 grams of zinc oxide. So when you have a limiting reactant problem, you have to work out 2 problems, 1 for each reactant. And the very last step then, Billy, we compare them. 349, 181. The smaller one is the one that we're going to run out of first. So this, 181, that's my maximum. That's the maximum amount of zinc oxide I can produce. Which means that I will run out of oxygen first. I'm going to run out of oxygen first, that's the limiting reactant. What's left over? The zinc sulfide. This is excess, leftover. So on those homework problems that some of you did over the weekend, if you didn't know what you're doing, go back and redo those problems, okay? Don't just be like, I tried them. That's good enough. No. Go back and redo them if you didn't know what you were doing. Practice makes perfect only if practice is perfect. In other words, if you're shooting free throws, it doesn't do you any good if you keep missing all the time. You don't get any points for attempting a free throw. You only get a point if you actually put it in the hoop. So practice makes perfect only if practice is perfect. You keep practicing until you get it in the hoop. And you keep doing it so you make sure that you get it in the hoop every single time. Because you don't get any points just for attempting it.
So 181 is the answer,
So the answer is 181.
because they would run off first.
Because it would run out first. Now, how would this problem change if I did it at 0 degrees Kelvin, no, not Kelvin, 0 degrees Celsius and 101.325 kPa? Yeah, awesome.
Just use that conversion.
We could use the molar conversion. Now you can still go through PV equals nRT if you wanted to, and change the pressure and change the temperature. But the quicker way would be to just say, okay, I'm at STP. I can use that molar volume. At STP, 185 liters, that's what we start with. If I'm at STP, 22.4 liters gives me 1 mole.
1 mole of what?
Whatever gas you're dealing with. In this case, it'd be oxygen. Is that your point?
Yes.
Touche.
Still don't label it for liters.
Where?
185.
Oh, come on, Michael. Be nice.
That's 2.
I caught that other one. I'll give you 1. But
What?
No, I
First we caught one.
he said this. He said there.
He said plural.
No, he didn't.
He
said
did. That
liters.
was
He
it.
Watch me rewind the tape.
Yep,
Yeah.
take a look.
Do it.
He
Do it.
wanted
Come on.
to.
Do it.
I'll give you a point for now, but I'm going to look on the tape and see. But anyhow, one last point I want to make is with the ideal gas equation. Where do we take into account that we're dealing with oxygen gas? Where does the actual type of gas fit into this equation?
What do you mean?
Do we have to do anything special because it's oxygen gas? No. That's the beauty, Chloe, of the ideal gas equation. It's the same for all gases.
That didn't mark.
It works for all gases. We don't care if it's oxygen gas, chlorine gas, methane gas. That's what makes it ideal. It works for all gases.